Hey everyone, I'm here this week with Jason Sanchez.
Hello.
Jason really loves random forests.
I do, and I think you will too.
He's sure of it. And so Jason's going to do a guest lecture today, and he's going to tell you all about random forests.
Yes, I use random forests in my work nearly every day, and I'm very excited to be able to show you how they work and how you could use them in your work as well.
All right, take it away, Jason.
Okay, see ya.
Hello everyone, I'm excited to do this guest lecture on random forests and how they are awesome. So, the main premise of this argument is that random forests should be the hammer of your data science toolkit. What are they? At a very high level, they're machine learning algorithms built for prediction. And they're some of the best algorithms out there you could have for prediction. We're going to cover the pros and cons list, which I made from an incredibly biased viewpoint. So the pros of random forests, they automatically model nonlinear relations and interactions between variables. Perfect linearity doesn't matter. So where this should jump out in your mind is your work with logistic regression and linear regression. We'll remember that those sort of models can only handle linear relationships between your x variables and your y variable. Random forests could handle all sorts of nonlinear and curious interactions automatically. You'll also remember that you had to drop a variable when you dummied out your categorical variables for fear of perfect linearity. With random forests, you don't have to do that, and we'll have some examples in this lecture that show that it just doesn't matter for random forests. Other pros of random forests is they're easy to tune. There are only a few settings that really matter. They're relatively easy to understand everything about them. So logistic regression and linear regression actually are very, very deep fields and deep algorithms where you could have many, many books on each one of them, and it would take several years to learn the intricacies of all of them. Random forests, you can learn essentially the entire algorithm, everything about them, rapidly. Also, random forests are flexible enough to handle regression and classification tasks, so you could use them for 90% of your data science problems. They're also useful as a step in exploratory data analysis to see which variables are important in your data set for prediction purposes. They can handle high-dimensional data. That means data sets that have more variables than observations. That's something else that linear regression and logistic regression cannot handle unless you have regularization built into them. They have a built-in method of checking to see model accuracy. So we've seen a holdout data set as a way to see how generalizable the error rate is in your model. We'll see that random forests actually have this method built in that let you get that, but still use all of your data. So generalize your model, see how accurate your model is, but still use all of your data. In general, random forests beat most other models at most prediction tasks. Now, I'm not going to claim they win in every instance, but 90-95% of cases, you could get a random forest to beat nearly any other model that's brought to the table. The cons, I have question marks there because really the random forest at minimum should be used as a benchmark model. So even if you are planning on building this very elegant, very sophisticated model later, you should start with a random forest because they're just so simple. To illustrate how simple these models are, we will run a few different models on the Boston housing dataset. So what we see here is I'm simply loading the Boston housing dataset. Mike told me you all have already worked with this dataset, so this should be familiar. This should also be familiar code, most of it where we're making a train and test split. Now what I did here, you could see I've imported numpy as np, and I've set this random seed. Random forests are based on a principle of randomness, which means every time you build the model, unlike in linear regression, the results might change slightly. So by setting this seed, I could ensure that the results I get with the random forest I build will be identical to the results you get when you're running this model and following along. So let's run this code. We're first going to turn on matplotlib, which lets us do charts, import that data, split the data, do super simple EDA. So I see that I have 506 observations in this data set and 13 variables. And let's start by building a linear regression model. Just a super basic as it gets, importing linear regression from the linear model library of scikit-learn, defining model as linear regression, keeping just all the defaults, fitting the data to the model, the training data, and then testing on the testing data set, and I'm outputting r squared. So let's see what we get, 0.76 r squared. Next, I'm going to train a simple decision tree. As we'll see later, random forests are a collection of decision trees. So this decision tree could represent one component, one small component of a random forest. And if you don't know what a decision tree is, that's okay. We'll cover that very soon. So we ran a decision tree and saw it did similar to linear regression, not much better. This amount that it did better could be due just to random luck. Now let's run a random forest model. And this is a random forest model with all of the defaults. So we could see that we just imported from scikit-learn ensemble random forest regressor. We defined the model. I set the random state here to be 42 just so that we could be sure that this result will be achieved by you as well. Fit the data to the model and then print the score. And what you could see is the code for all of these models is identical. The only real difference is the results. So you had two results, 76, 78 r squared, but for the random forest you got a 0.89 r squared out of the gate, which is very good. So we will next move on to the prerequisites, because to understand random forests you need to be able to understand decision trees and bootstrap sampling. See you in a sec.